Deep in the vast expanse of the universe, there exists a force so powerful that it's pulling entire galaxies toward it. A gravitational anomaly so mysterious that scientists have named it the Great Attractor. This cosmic enigma is just one of many unusual anomalies scattered across the fabric of space, each defying our current understanding of physics and cosmology. From colossal voids where galaxies refuse to form, to bizarre quantum fluctuations that hint at parallel realities, these anomalies aren't just oddities, they're clues. Clues that could unlock the secrets of dark matter, reshape our understanding of the multiverse, and perhaps even reveal the true nature of reality itself. Today, we're diving into the most perplexing anomalies modern science has uncovered, exploring how they challenge everything we think we know about the cosmos. What if these cosmic puzzles hold the answers to questions we've barely begun to ask? Let's find out. Deep within the Centaurus constellation, far beyond the familiar glow of stars we see from Earth, lies one of the most baffling phenomena in the universe, the Great Attractor. Imagine a force so immense that it's dragging entire galaxies, including our own Milky Way, toward it at speeds exceeding 1,000 kilometers per second. This gravitational powerhouse, first discovered in the 1970s, wasn't something scientists could see directly. Instead, they noticed something strange. Galaxies in our cosmic neighborhood were all moving in the same direction, as if being pulled by an invisible hand. This observation hinted at the existence of a massive, hidden structure, a cosmic magnet of sorts, lurking in the darkness. But what exactly is the Great Attractor? For decades, it's been shrouded in mystery. Some researchers believe it's a supercluster, a dense collection of galaxies bound together by gravity. Others argue it could be something far more exotic, perhaps a region where dark matter is concentrated in ways we don't yet understand. Dark matter, that elusive substance that makes up about 85% of the universe's mass, is thought to play a key role in this phenomenon. It's the glue holding galaxies together, and its gravitational pull could explain why the Great Attractor exerts such a powerful influence over its surroundings. Yet, studying this anomaly isn't easy. Our view of the Great Attractor is partially blocked by the Milky Way's own disk of stars and dust, making it a cosmic blind spot. That's where tools like the Hubble Space Telescope and the James Webb Space Telescope come in. These observatories are peering through the obscuring veil, gathering data that could help us unravel the secrets of this gravitational giant. Even with these advancements, the Great Attractor continues to challenge our understanding of gravity, dark matter, and the large-scale structure of the universe. And the mystery deepens. Some scientists speculate that the Great Attractor might not be the ultimate source of this gravitational pull. Instead, it could be just one piece of a much larger puzzle, a stepping stone leading to an even greater anomaly far beyond our current reach. As we continue to study this cosmic enigma, it raises a tantalizing question. What other gravitational anomalies are out there waiting to be discovered? These anomalies don't just defy explanation, they invite us to rethink what we know about the cosmos. And as we'll see next, the Great Attractor is just the beginning of the strange and wonderful phenomena hidden in the fabric of space. While the Great Attractor remains a gravitational enigma, another cosmic mystery has been quietly unfolding, one that hints at forces far beyond the limits of our observable universe. This phenomenon, known as dark flow, describes the peculiar motion of galaxy clusters, all moving in the same direction, as if swept along by an unseen cosmic current. It's as if the universe itself has a hidden undercurrent, tugging at the fabric of space in ways we're only beginning to comprehend. The discovery of dark flow came from an unlikely source, the cosmic microwave background radiation, or CMB. This faint afterglow of the Big Bang serves as a snapshot of the early universe, a treasure trove of information about its origins and evolution. By studying tiny temperature fluctuations in the CMB, scientists noticed something extraordinary. Galaxy clusters spread across vast distances appeared to be moving toward a specific region of space, a region that lies far beyond the edge of what we can see. This motion defies the expected behavior of galaxies, which should be evenly distributed and moving in all directions due to the universe's expansion. Instead, dark flow suggests the presence of an immense gravitational influence, one that originates from beyond our cosmic horizon. So, what could be causing this mysterious motion? One leading theory points to the possibility of massive structures lurking in the unobservable regions of the universe. These structures, far larger than anything we've encountered, might exert a gravitational pull strong enough to drag entire galaxy clusters toward them. Another, even more tantalizing idea is that dark flow could be evidence of parallel universes. In a multiverse scenario, neighboring universes, each with their own physical laws and structures, might interact with ours in ways we can't yet fully understand. The gravitational influence from these other realms could be the unseen force behind dark flow, offering a glimpse into a reality far grander than we've ever imagined. But dark flow isn't just a theoretical curiosity. It has profound implications for our understanding of cosmology. If confirmed, it would challenge the long-held assumption that the universe is uniform and isotropic, meaning it looks the same in all directions. Instead, it suggests that there are large-scale asymmetries in the cosmos, with regions of space behaving in ways that defy our current models. This raises the question, how much of the universe are we truly seeing? And what lies beyond the boundaries of our observation? As we grapple with these questions, dark flow serves as a reminder of how much we still have to learn about the cosmos. It's a phenomenon that pushes the limits of our knowledge, inviting us to explore the unknown and rethink our place in the universe. But the mysteries don't stop there. Just as dark flow reveals the influence of unseen forces, another cosmic anomaly, vast, empty regions known as cosmic voids, challenges our understanding of space in a completely different way. These voids, stretching millions of light-years across, are places where galaxies are conspicuously absent, creating pockets of emptiness that defy our expectations of how the universe should be structured. What secrets do these voids hold, and how do they shape the cosmos as we know it? Amid the crowded tapestry of galaxies, stars, and cosmic structures, there exists a stark contrast, vast, empty regions where the universe seems to hold its breath. These are cosmic voids, unimaginably large pockets of space that stretch hundreds of millions of light-years across, containing little to no matter. Far from being mere blank spots on the cosmic map, these voids play a crucial role in shaping the universe as we know it. They are the silent architects of the large-scale structure of the cosmos, influencing how galaxies cluster and how the universe expands over time. One of the most famous examples is the Boötes Void, a colossal region of emptiness spanning approximately 330 million light-years. Named after the constellation in which it lies, the Boötes Void is so vast that if the Milky Way were placed at its center, we'd see almost nothing in every direction for millions of light-years. This near-total absence of galaxies defies our expectations, as the universe is generally thought to have a relatively even distribution of matter. Yet, here we find a gaping hole, a place where the rules of cosmic density seem to break down. So, how do these voids form? The answer lies in the early universe, during a time when tiny fluctuations in density set the stage for everything we see today. In regions where matter was slightly less concentrated, gravity couldn't pull enough material together to form galaxies. Over billions of years, these underdense regions expanded, creating the voids we observe now. Meanwhile, the denser areas became the web-like structures of galaxies and galaxy clusters, with the voids acting as the empty spaces between the threads. But cosmic voids aren't just empty. They are filled with a sparse scattering of gas and dark matter, and their emptiness actually exerts a powerful influence on the universe. As the universe expands, voids grow larger, and their low-density environment allows space itself to stretch more rapidly than in denser regions. This uneven expansion contributes to the overall acceleration of the universe, a phenomenon often attributed to dark energy. In this way, voids are not just passive gaps, they're active players in the cosmic dance, shaping the fate of the universe on the grandest scales. What lies within these voids is another intriguing question. Some theories suggest they could contain isolated galaxies or even exotic objects we haven't yet detected. Others propose that voids might harbor clues about dark energy or the nature of the early universe. Studying these regions could reveal insights into how the cosmos evolved and why it looks the way it does today. As we peer into these vast expanses of nothingness, we're reminded that the universe is full of surprises. Cosmic voids challenge our assumptions about the distribution of matter and the forces that shape the cosmos. But while these enormous empty spaces dominate the large-scale structure of the universe, there are other anomalies that occur on much smaller scales, phenomena so tiny and fleeting that they blur the line between reality and possibility. These are quantum fluctuations, the minute ripples in the fabric of space-time that hint at a universe far stranger than we can imagine. What do these fluctuations tell us about the nature of reality, and how do they connect to the cosmic voids that stretch across the heavens? Let's explore. At the heart of the universe's grand design lies a phenomenon so subtle that it's nearly invisible, yet its effects ripple across the cosmos, shaping everything from the tiniest particles to the largest galaxies. These are quantum fluctuations, the spontaneous, random changes in energy that occur even in the complete absence of matter. Imagine a perfectly still pond, its surface smooth and undisturbed. Now picture tiny ripples suddenly appearing, seemingly out of nowhere. These ripples don't come from wind or a thrown stone, they simply happen. This is the essence of quantum fluctuations, tiny, unpredictable shifts in energy that arise even in the vacuum of space, as predicted by the strange and fascinating laws of quantum mechanics. What makes these fluctuations so remarkable is their profound impact on the universe. In the earliest moments after the Big Bang, the cosmos was a seething cauldron of energy and matter. Quantum fluctuations, then just microscopic ripples, served as the seeds for the vast structures we see today. Over billions of years, these tiny variations in density grew, pulled together by gravity, eventually giving rise to galaxies, galaxy clusters, and the intricate cosmic web that spans the universe. Without these fluctuations, the cosmos might have remained a bland, featureless expanse, a universe devoid of stars, planets, or life. In a very real sense, the galaxies we see today are the echoes of these ancient, minuscule ripples. But quantum fluctuations don't just belong to the distant past, they're happening all around us, even in what we think of as empty space. According to quantum field theory, a vacuum isn't truly empty. Instead, it's a seething, bubbling sea of virtual particles that pop in and out of existence in fleeting moments. These particles are the result of quantum fluctuations, and their presence suggests that the very fabric of space is far more dynamic and alive than we might imagine. This challenges our classical notion of emptiness, revealing a universe where even the void is teeming with activity. The implications of quantum fluctuations stretch far beyond the birth of galaxies. They also offer clues about the nature of spacetime itself. Just as massive objects like stars and black holes warp the fabric of space, so too do these tiny fluctuations leave their mark. They hint at a universe where space and time are not static and unchanging, but are instead constantly shifting, bending, and evolving. This dynamic nature of space-time opens the door to some of the most profound questions in physics. What is the true nature of reality? And how do these microscopic ripples connect to the vast cosmic structures we observe? As we explore these questions, we're led to another astonishing phenomenon: the way massive objects warp spacetime itself, creating the extreme conditions that give rise to black holes. These cosmic behemoths, with their immense gravitational pull, are the ultimate expression of how matter and energy can distort the fabric of the universe. But how do black holes form, and what happens when spacetime is stretched to its limits? The answers lie in the interplay between quantum fluctuations and the immense forces of gravity, a dance that continues to shape the cosmos in ways we're only beginning to understand. In the vast theater of the cosmos, few phenomena capture the imagination quite like black holes, regions of spacetime so warped that not even light can escape their grasp. These cosmic behemoths are the ultimate anomalies, places where the laws of physics as we know them break down, and the very fabric of reality is stretched to its limits. But what exactly are black holes, and how do they come to exist in the first place? The story begins with the death of massive stars. When a star many times more massive than our Sun exhausts its nuclear fuel, it can no longer withstand the crushing force of its own gravity. The star collapses inward in a spectacular supernova explosion, leaving behind a core so dense that it forms a black hole. This process creates a gravitational field so intense that it warps spacetime itself, creating a boundary known as the event horizon, a point of no return where escape becomes impossible. The event horizon is one of the most fascinating aspects of a black hole. It's the ultimate cosmic threshold, a one-way door where the usual rules of space and time cease to apply. Once something crosses this boundary, it's lost to the outside universe forever, pulled inexorably toward the black hole's core, a point of infinite density known as the singularity. Here, the laws of physics as we understand them break down completely. Gravity becomes infinitely strong, space-time curves to an extreme degree, and our current theories simply cannot describe what happens. It's a realm where the known and the unknown collide, challenging scientists to rethink the very foundations of physics. But black holes aren't just destructive forces, they're also cosmic laboratories, offering clues about the nature of the universe. In 2019, the Event Horizon Telescope made history by capturing the first ever image of a black hole's shadow, located in the galaxy Messier 87. This groundbreaking achievement provided a glimpse of the event horizon itself, confirming predictions made by Einstein's theory of general relativity. The image revealed a glowing ring of light created by superheated gas swirling around the black hole, and a dark central region where light vanishes into the void. This discovery not only confirmed the existence of black holes, but also opened new avenues for studying their properties and behavior. Black holes also play a crucial role in shaping the universe on a grand scale. At the center of nearly every galaxy, including our own Milky Way, lies a supermassive black hole, a colossal object millions or even billions of times more massive than the Sun. These giants are thought to influence the formation and evolution of galaxies, their immense gravitational pull shaping the motion of stars and gas around them. Some researchers even speculate that black holes could be connected to dark matter, the mysterious substance that makes up most of the universe's mass. While the exact relationship remains unclear, studying black holes could provide vital clues about this elusive component of the cosmos. Yet for all we've learned, black holes remain shrouded in mystery. What lies beyond the event horizon? What happens to matter as it approaches the singularity? these questions push the boundaries of our knowledge, inspiring both awe and curiosity. And as we ponder these cosmic enigmas, another tantalizing possibility emerges. Could black holes hold the key to traversing the universe? This idea leads us to the concept of wormholes, theoretical tunnels through spacetime that could connect distant parts of the cosmos. While wormholes remain speculative, they represent yet another anomaly in the fabric of space, one that could redefine our understanding of travel, time, and the very structure of reality. Imagine a shortcut through the universe, a tunnel that could whisk you across billions of light years in an instant, bypassing the vast emptiness of space. This is the tantalizing idea behind wormholes, hypothetical bridges through spacetime that could connect distant regions of the cosmos or even entirely different universes. While wormholes remain firmly in the realm of theory, they're not just science fiction. These cosmic shortcuts emerge from the equations of general relativity, the same framework that describes black holes and the curvature of spacetime. According to Einstein's theory, massive objects like stars and planets warp the fabric of space and time, creating the gravitational effects we observe. Wormholes take this idea a step further, suggesting that spacetime could fold in such a way that two distant points are brought close together, forming a tunnel, a shortcut through the cosmic landscape. The concept of wormholes is both thrilling and perplexing. On one hand, they offer the possibility of faster-than-light travel, allowing us to traverse the universe without being bound by the speed of light. On the other hand, they raise profound questions about the nature of reality. For instance, if a wormhole connects 2 points in spacetime, could it also connect 2 different moments in time? This idea opens the door to the possibility of time travel, a notion that has captivated scientists and storytellers alike. But time travel isn't the only paradox wormholes could create. They also introduce the potential for causality violations, situations where cause and effect become entangled in ways that defy our understanding of how events unfold. Despite their theoretical appeal, wormholes face significant challenges. One of the biggest hurdles is their stability. According to current models, wormholes would require exotic matter, a substance with negative energy, to keep them from collapsing. This exotic matter, which has never been observed in nature, would need to counteract the immense gravitational forces that would otherwise close the tunnel. Without it, a wormhole would snap shut almost instantly, making it impossible to traverse. Even if such matter exists, the energy required to create and sustain a wormhole would be beyond anything we can currently imagine. The speculative nature of wormholes hasn't stopped scientists from exploring their potential. Some researchers have proposed that microscopic wormholes could exist at the quantum level, popping in and out of existence in the seething foam of spacetime. These tiny tunnels, though far too small for any form of travel, could offer clues about the quantum structure of the universe. Others have theorized that wormholes might be connected to black holes, forming a network of cosmic gateways that could link distant parts of the cosmos. While these ideas remain unproven, they inspire us to think beyond the boundaries of our current knowledge. As we ponder the mysteries of wormholes, another intriguing concept comes into focus: white holes. Often described as the theoretical opposites of black holes, white holes are regions of spacetime where matter and energy can only escape, never enter. While no white holes have ever been observed, they emerge from the same equations that predict black holes and wormholes. Some scientists speculate that a white hole could be connected to a black hole via a wormhole, forming a cosmic bridge between 2 points in spacetime. This idea, while speculative, adds another layer of complexity to our understanding of the universe's most extreme phenomena. Wormholes and white holes remind us that the universe is far stranger than we can imagine. These theoretical constructs challenge our understanding of space, time, and the very fabric of reality. They invite us to explore the boundaries of what's possible, pushing the limits of science and imagination. But as we venture into these speculative realms, another question arises. What other cosmic anomalies are waiting to be discovered? From the depths of black holes to the vast emptiness of cosmic voids, the universe continues to reveal its secrets, one mystery at a time. If black holes are the cosmic vacuum cleaners of the universe, relentlessly pulling in matter and light, then white holes are their polar opposites, theoretical objects that defy gravity by spewing out matter and energy instead of consuming them. Picture a fountain in the middle of space, endlessly ejecting streams of light and particles into the cosmos. This is the essence of a white hole, a region of spacetime where nothing can enter but everything can escape. While black holes are well-documented cosmic phenomena, white holes remain firmly in the realm of theory, born from the same equations that describe their darker counterparts. The concept of white holes emerged from Einstein's theory of general relativity, which describes how massive objects warp the fabric of spacetime. When scientists solved these equations, they found solutions that not only predicted black holes but also their hypothetical opposites. Unlike black holes, which form from the collapse of massive stars, white holes are thought to be regions where matter and energy are expelled outward, as if the universe itself were pushing back against gravity. However, despite their intriguing properties, no observational evidence for white holes has ever been found, leaving their existence as one of the great mysteries of modern physics. One of the most fascinating ideas about white holes is their potential connection to black holes. Some theories suggest that a black hole and a white hole could be linked through a wormhole, forming a cosmic recycling system. In this scenario, matter and energy swallowed by a black hole could emerge from a white hole in another part of the universe, or even in a different universe altogether. This concept paints a picture of the cosmos as a vast, interconnected network, where spacetime itself acts as a bridge between distant regions. While this idea is purely speculative, it offers a glimpse into how the universe might operate on scales far beyond our current understanding. The speculative nature of white holes doesn't diminish their significance. In fact, they challenge us to rethink the fundamental principles of spacetime and gravity. If white holes exist, they could provide insights into the nature of singularities, the infinitely dense cores of black holes, and the behavior of spacetime in extreme conditions. They also raise intriguing questions about the arrow of time. While black holes represent a one-way journey into the unknown, white holes suggest the possibility of a reversal, a cosmic rewind that defies our everyday experience of cause and effect. As we explore these theoretical constructs, we're reminded of how much of the universe remains hidden from view. White holes, like wormholes and black holes, push the boundaries of our knowledge, inviting us to imagine a cosmos far stranger and more interconnected than we've ever imagined. But while these anomalies captivate our imagination, they're just one piece of the cosmic puzzle. Another mysterious force is at work on an even grander scale, shaping the very fabric of the universe itself. This force, dark energy, is driving the accelerated expansion of the cosmos, pulling galaxies apart at ever-increasing speeds. What is this enigmatic energy, and how does it fit into the broader tapestry of the universe? Let's take a closer look. The universe is expanding, but not in the way you might expect. Instead of slowing down over time as gravity pulls galaxies together, the cosmos is stretching faster and faster, an acceleration driven by a mysterious force called dark energy. This unseen power, which makes up about 68% of the universe, is one of the most profound mysteries in modern science. It's the reason our universe isn't just growing, it's racing outward, pushing galaxies apart at speeds that defy the pull of gravity itself. But what exactly is dark energy, and how did we discover something so elusive? the story of dark energy begins with a groundbreaking discovery in the late 1990s. Astronomers were studying distant supernovae, exploding stars whose brightness serves as a cosmic yardstick, when they noticed something strange. These supernovae appeared dimmer than expected, suggesting they were farther away than they should be. The only explanation: the universe wasn't just expanding, it was accelerating. This revelation turned cosmology on its head. For decades, scientists had assumed that gravity would eventually slow the universe's expansion, but dark energy was doing the opposite, acting as a kind of anti-gravity that pushes space itself apart. So, what is dark energy? The truth is, we don't fully know. What we do understand is that it behaves unlike anything else in the cosmos. One of its defining properties is negative pressure, a force that counteracts gravity on the largest scales. Imagine blowing up a balloon, but instead of the rubber stretching, it's the space inside the balloon that's actively pushing outward. That's the effect dark energy has on the universe. It's not just expanding space, it's accelerating the expansion, stretching the fabric of reality faster and faster over time. One of the leading explanations for dark energy is the cosmological constant, a concept first proposed by Albert Einstein. Originally introduced to balance his equations and describe a static universe, Einstein later dismissed the cosmological constant as his greatest blunder when the universe's expansion was discovered. But now it's back in the spotlight as a possible explanation for dark energy. The cosmological constant suggests that empty space itself has an inherent energy density, a kind of background hum that drives the universe's acceleration. While this idea fits many observations, it raises new questions, such as why the energy density is so small yet so impactful. Another intriguing theory is quintessence, a dynamic form of dark energy that changes over time. Unlike the cosmological constant, which remains steady, quintessence could vary in strength, potentially offering clues about the universe's past and future. Some models even suggest that dark energy might interact with dark matter, the invisible substance that makes up most of the universe's mass. This interplay could shape the fate of the cosmos, determining whether the universe continues to expand indefinitely, collapses back on itself, or even tears apart in a big rip. The existence of dark energy challenges our understanding of gravity and the fundamental forces that govern the universe. It also raises profound questions about the cosmos's ultimate fate. Will dark energy continue to dominate, stretching space until galaxies are so far apart that the night sky becomes a void? Or could its influence wane, allowing gravity to regain control? These questions remind us that the universe is still full of surprises, and dark energy is one of its most tantalizing mysteries. But dark energy isn't the only invisible force shaping the cosmos. Just as it drives the universe's expansion, another elusive component, dark matter, holds galaxies together, acting as the cosmic glue that binds the universe. Together, these two invisible forces dominate the universe, yet we've only just begun to understand their roles. What is dark matter, and how does it shape the galaxies we see today? Let's explore. While dark energy drives the universe's expansion, another invisible force quietly holds the cosmos together: dark matter. This mysterious substance, which makes up about 27% of the universe, is unlike anything we've ever encountered. It doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. Yet, its presence is undeniable, revealed through the gravitational effects it exerts on the visible universe. Without dark matter, galaxies would fly apart, and the intricate cosmic web that structures the universe would unravel. So, what exactly is dark matter, and how do we know it's there? The story of dark matter begins with a puzzle. In the 1930s, astronomer Fritz Zwicky observed that galaxies in the Coma cluster were moving far too quickly to be held together by the gravity of their visible stars alone. He proposed the existence of unseen matter, what we now call dark matter, to account for this discrepancy. Decades later, Vera Rubin's groundbreaking work on galaxy rotation curves confirmed Zwicky's suspicions. She found that stars on the outskirts of galaxies were orbiting just as fast as those near the center, a phenomenon that only made sense if there was a massive halo of invisible matter surrounding each galaxy. This discovery cemented dark matter as a fundamental component of the cosmos. But what is dark matter made of? The leading theory suggests it's composed of weakly interacting massive particles, or WIMP hypothetical particles that rarely interact with ordinary matter. These elusive particles would pass through Earth as if it weren't there, making them incredibly difficult to detect. To catch a glimpse of dark matter, scientists have devised ingenious experiments. Underground detectors, shielded from cosmic rays, wait for the faintest signal of a WIMP colliding with an atom. Meanwhile, the Large Hadron Collider smashes particles together at unimaginable speeds, hoping to create dark matter in the lab. Despite decades of searching, dark matter has yet to reveal itself, leaving scientists to refine their methods and explore alternative theories. The role of dark matter goes far beyond holding galaxies together. It's also the cosmic scaffolding upon which the universe is built. In the early universe, dark matter clumped together under gravity, forming the seeds of galaxies and galaxy clusters. Ordinary matter, drawn by dark matter's gravitational pull, eventually coalesced into stars and planets. Without dark matter, the universe as we know it wouldn't exist. Yet, for all its importance, dark matter remains one of the greatest unsolved mysteries in science. Why doesn't it interact with light? What are its fundamental properties? These questions drive some of the most ambitious experiments in physics today. As we continue to search for answers, another intriguing possibility emerges. Could dark matter be connected to other cosmic anomalies? Some researchers have speculated that dark matter might interact with itself in ways we don't yet understand, creating structures or even exotic particles we've yet to detect. Others have proposed that dark matter could be linked to the quantum foam of spacetime, suggesting a deeper connection between the microscopic and cosmic scales. While these ideas remain speculative, they remind us that the universe is full of surprises waiting to be uncovered. But dark matter isn't the only theoretical construct that challenges our understanding of the cosmos. Another fascinating anomaly lies in the realm of spacetime itself, cosmic strings. These hypothetical one-dimensional defects, thought to have formed in the early universe, are like cracks in the fabric of reality. Stretching across unimaginable distances, cosmic strings could warp spacetime, creating ripples that might one day be detected. What are these cosmic strings, and how do they fit into the broader tapestry of the universe? Let's explore. Picture the early universe as a cosmic forge, a seething, chaotic environment where the laws of physics were still taking shape. In this primordial crucible, immense energy fluctuations and phase transitions could have left behind strange remnants, defects in the fabric of spacetime itself. Among these remnants are cosmic strings, theoretical one-dimensional structures that stretch across the universe like cracks in a frozen lake. Unlike black holes or wormholes, cosmic strings aren't tied to massive objects or exotic matter. Instead, they're thought to be pure distortions in spacetime, formed during the rapid cooling of the early universe when the fundamental forces separated into what we know today. Cosmic strings are incredibly thin, just 1 atom wide, but unimaginably dense, with masses that could rival entire galaxies packed into their minuscule width. Despite their size, they're not static. These strings can vibrate, snap, or even loop back on themselves, creating ripples in spacetime that could have profound effects on the cosmos. For instance, if a cosmic string were to pass through a region of space, it could distort the path of light, creating a phenomenon known as gravitational lensing. This effect, where light bends around massive objects, is well documented around galaxies and black holes, but the lensing caused by a cosmic string would be far more precise and distinctive, leaving behind a telltale signature in the form of double images of distant objects. Another potential clue to the existence of cosmic strings lies in the cosmic microwave background, or CMB, the faint afterglow of the Big Bang. The rapid movements of cosmic strings could have generated tiny temperature fluctuations in the CMB, leaving faint imprints that scientists might one day detect. These imprints would be different from the patterns created by other cosmic phenomena, offering a unique fingerprint of these spacetime defects. While no definitive evidence of cosmic strings has been found yet, their theoretical existence is deeply tied to our understanding of the early universe, particularly during the phase transitions that occurred as the universe cooled and expanded. The formation of cosmic strings is thought to be linked to symmetry breaking, a process that occurred when the universe transitioned from a state of higher symmetry to one of lower symmetry. Imagine a pot of water cooling down. As it reaches freezing point, the water molecules arrange themselves into a crystalline structure, breaking the uniform symmetry of the liquid. Similarly, during the early universe, as temperatures dropped, the fundamental forces and particles underwent phase transitions that could have created topological defects like cosmic strings. These defects are essentially frozen remnants of the universe's earlier, more symmetrical state preserved in the fabric of spacetime. Detecting cosmic strings, however, is no easy task. Their incredibly thin and subtle nature makes them nearly invisible to our current observational tools. Yet, their potential effects on spacetime and the CMB offer tantalizing opportunities for discovery. Some scientists have even proposed that cosmic strings could be detected through their gravitational wave emissions, ripples in spacetime caused by their vibrations or collisions. If such signals were observed, they could provide direct evidence of these cosmic threads, offering a glimpse into the universe's earliest moments. The study of cosmic strings isn't just about uncovering these elusive structures. It's also about understanding the fundamental nature of spacetime itself. These one-dimensional rips challenge our perception of the universe's fabric, suggesting that spacetime isn't just a smooth, continuous surface, but can also contain defects and imperfections. As we explore these ideas, we're led to another fascinating theoretical construct from the early universe: magnetic monopoles. These hypothetical particles, which carry a single magnetic charge, could also be remnants of the universe's formative moments, offering yet another piece of the cosmic puzzle. What are magnetic monopoles, and how do they fit into the story of the universe's origins? Let's find out. Imagine trying to solve a puzzle where one of the most important pieces is missing, a piece so crucial that without it, the picture remains incomplete. In the realm of particle physics, magnetic monopoles are that elusive piece. These hypothetical particles, predicted by grand unified theories, are unlike anything we've ever encountered. While every magnet we know has two poles, a north and a south, a magnetic monopole would have just one, either north or south, but never both. This idea, though seemingly simple, challenges one of the most fundamental principles of electromagnetism, a cornerstone of modern physics. If magnetic monopoles exist, they could revolutionize our understanding of the universe, offering insights into everything from the forces that govern particles to the very fabric of spacetime. The concept of magnetic monopoles dates back to the early 20th century, when physicist Paul Dirac first proposed their existence. Dirac's equations suggested that if even a single magnetic monopole existed, it would explain why electric charge comes in discrete, quantized units, a phenomenon that had puzzled scientists for decades. But despite their theoretical elegance, magnetic monopoles have remained frustratingly out of reach. No experiment has ever definitively detected one, leaving them as one of the great what-ifs of modern science. So, where could these monopoles be hiding, and why are they so hard to find? One possibility lies in the early universe. During the moments following the Big Bang, the universe was a hot, dense soup of energy and particles. As it expanded and cooled, phase transitions occurred akin to water freezing into ice that could have created magnetic monopoles as topological defects in spacetime. These defects, much like the cracks that form in ice as it freezes, might have left behind remnants that still exist today. If so, they could be scattered throughout the cosmos, lurking in the vast emptiness of space or even within the Earth itself. But detecting them is no small feat. Magnetic monopoles, if they exist, would be incredibly rare and interact weakly with ordinary matter, making them nearly invisible to our current detection methods. The search for magnetic monopoles has led scientists to some creative and ambitious experiments. Deep underground, shielded from cosmic rays, detectors wait for the faintest sign of a monopole passing through. In particle accelerators like the Large Hadron Collider, researchers smash particles together at incredible speeds, hoping to create a monopole in the lab. Even natural phenomena such as cosmic rays or ancient minerals have been scrutinized for traces of these elusive particles. Despite these efforts, the search continues, driven by the tantalizing possibility that magnetic monopoles could unlock new frontiers in physics. If magnetic monopoles do exist, their implications would be profound. They could provide a missing link between electricity and magnetism, offering a more unified picture of the fundamental forces. In grand unified theories, which aim to merge the electromagnetic, weak, and strong nuclear forces into a single framework, monopoles play a crucial role. Their discovery could validate these theories, shedding light on the universe's earliest moments and the forces that shaped it. Beyond that, magnetic monopoles might even hold clues about the nature of spacetime itself, suggesting that the universe's fabric is far more intricate than we've imagined. But the mystery of magnetic monopoles doesn't end with their potential existence. It also raises questions about the nature of reality and the limits of our understanding. If something as fundamental as magnetism can have a single pole, what other symmetries in physics might be broken? Could there be other hidden particles or forces waiting to be discovered? These questions remind us that the universe is full of surprises, and that even the most well-established theories can be challenged by a single, elusive anomaly. As we ponder the mysteries of magnetic monopoles, another strange and fascinating phenomenon comes into focus: quantum entanglement. This bizarre behavior, where particles become inextricably linked across vast distances, defies our classical understanding of physics. If magnetic monopoles challenge our notions of electromagnetism, quantum entanglement shakes the very foundations of reality itself. What is this strange connection between particles, and how does it fit into the larger tapestry of the universe? Let's explore. Imagine two particles born together in a single moment, forever linked by an invisible thread that defies the very fabric of space and time. No matter how far apart they are, whether separated by a millimeter or the width of a galaxy, the state of one particle instantly influences the state of the other. This phenomenon, known as quantum entanglement, is one of the most baffling and fascinating aspects of quantum mechanics. Albert Einstein famously called it spooky action at a distance, a description that captures both its mystery and its defiance of classical physics. But what exactly is quantum entanglement, and why does it shake the foundations of our understanding of reality? At its core, quantum entanglement occurs when two or more particles become so deeply connected that their properties like spin, position, or momentum are intertwined. When you measure one particle, you instantly know the state of the other, no matter how far apart they are. This connection happens faster than the speed of light, seemingly violating the principle of locality, which states that objects are only influenced by their immediate surroundings. For Einstein, this was deeply unsettling. He believed that nothing could travel faster than light, and he saw entanglement as evidence that quantum mechanics was incomplete. Yet, decades of experiments have confirmed that entanglement is very real and very strange. One of the most famous experiments to test entanglement is the Bell test, named after physicist John Bell. The test involves creating entangled particles, sending them to distant locations, and measuring their properties. If the results match in a way that classical physics can't explain, it proves the particles are truly entangled. In the 1980s, physicist Elaine Aspect conducted groundbreaking Bell tests that showed entanglement was real, defying Einstein's skepticism. More recently, experiments have entangled particles over distances of hundreds of kilometers, even using satellites to beam entangled photons across continents. These experiments confirm that entanglement isn't just a quirk of the lab, it's a fundamental feature of the universe. But what makes entanglement so revolutionary isn't just its defiance of classical physics. It's also the potential it holds for transforming technology. Quantum entanglement is the backbone of quantum computing, a new frontier in computing that could solve problems far beyond the reach of classical computers. In a quantum computer, entangled qubits, quantum bits, can perform calculations in parallel, exponentially increasing processing power. This could revolutionize fields like cryptography, drug discovery, and artificial intelligence. Entanglement also underpins quantum communication, enabling ultra-secure networks that are virtually impossible to hack. By harnessing this spooky action, we're on the brink of a technological revolution. Yet, entanglement doesn't just change how we think about technology, it challenges how we think about reality itself. If particles can instantaneously influence each other across vast distances, what does that mean for our understanding of space and time? Some physicists suggest that entanglement hints at a deeper, hidden layer of reality, where the universe is more interconnected than we can perceive. Others propose that entanglement might be a clue to the holographic principle, a radical theory that suggests our three-dimensional universe could be a projection of information stored on a two-dimensional surface. Could entanglement be the thread that ties this holographic universe together? As we explore these ideas, we're reminded that the universe is far stranger than we can imagine. Quantum entanglement, with its instant connections and mysterious implications, invites us to rethink the very nature of reality. And just as entanglement challenges our understanding of space and time, the holographic principle takes this idea even further, suggesting that the universe itself might be a kind of cosmic illusion. What does this mean for our place in the cosmos, and how does it reshape our understanding of existence? Let's take a closer look. The universe, as we perceive it, might be nothing more than an illusion, a cosmic mirage projected from a lower dimensional surface. This radical idea, known as the holographic principle, challenges our most fundamental understanding of reality. At its core, the holographic principle suggests that all the information contained within a volume of space can be encoded on its boundary, much like a hologram encodes a three-dimensional image on a two-dimensional surface. It's a concept so profound that it blurs the line between science and philosophy, forcing us to reconsider what it means to exist in a universe that might be far simpler and far stranger than we've ever imagined. The origins of the holographic principle lie in the study of black holes, those cosmic enigmas that warp spacetime to its limits. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking made a startling discovery. The entropy of a black hole, a measure of its information content, is proportional to the area of its event horizon, not its volume. This finding hinted at a profound connection between the surface of a black hole and the information within it, suggesting that the three-dimensional reality we experience might be encoded on a two-dimensional boundary. This idea was later formalized by physicist Gerard T. Hooft and expanded upon by Leonard Susskind, who proposed that the entire universe could be described as a hologram, a projection from a lower dimensional surface. But how does this work? Imagine standing in front of a movie screen. What you see is a flat, two-dimensional surface, yet the images projected onto it create the illusion of depth, movement, and life. The holographic principle suggests that our universe operates in a similar way. The three-dimensional world we experience, with its galaxies, stars, and planets, might be a projection from a two-dimensional boundary at the edge of the cosmos. This boundary, often referred to as the cosmic horizon, encodes all the information needed to reconstruct our reality. It's a mind-bending idea, one that suggests the universe is far more economical with information than we ever realized. The implications of the holographic principle are as far-reaching as they are radical. If true, it could mean that spacetime itself is emergent, a secondary phenomenon that arises from the interactions of information encoded on a lower dimensional surface. This challenges the very notion of spacetime as a fundamental building block of the universe, suggesting instead that it's a kind of illusion, a holographic projection that emerges from deeper, more fundamental layers of reality. It's a perspective that unifies the microscopic and the macroscopic, offering a potential bridge between quantum mechanics and general relativity, two theories that have long resisted unification. Yet, the holographic principle isn't just a theoretical curiosity. It has profound implications for our understanding of black holes, the nature of information, and even the origins of the universe. For instance, it suggests that the information swallowed by a black hole isn't lost forever, but is instead encoded on its event horizon, waiting to be decoded in some future state. This idea has sparked intense debate and research, leading to new insights into the paradoxes of black hole physics and the nature of entropy. As we grapple with the implications of the holographic principle, another tantalizing possibility emerges. Could this principle extend beyond our universe? This idea brings us to the concept of the multiverse, a theory proposing that our universe is just one of many, each with its own physical laws and properties. If the holographic principle holds true, could these other universes also be projections from lower dimensional boundaries? And if so, what does that mean for the nature of reality itself? The answers to these questions might lie in the interplay between the holographic principle and the multiverse, opening the door to a cosmos far more interconnected and far more mysterious than we've ever imagined. If the universe is a cosmic stage, then the multiverse theory suggests that it might not be the only performance in town. This idea, that our universe is just one of many, each with its own unique set of physical laws and properties, has captivated scientists and storytellers alike. It's a concept that stretches the boundaries of imagination, challenging us to think beyond the confines of our observable reality. But is the multiverse more than just a fascinating idea? Could it be a real framework for understanding the cosmos? Let's dive into this mind-bending theory and explore what it means for our place in the universe. The multiverse isn't a single, unified concept, it's a collection of ideas, each proposing a different way multiple universes might exist. One of the most widely discussed versions is the inflationary multiverse, rooted in the theory of cosmic inflation. This theory suggests that shortly after the Big Bang, space expanded exponentially, creating vast regions that evolved into separate universes. In this scenario, our universe is just one bubble in an endless cosmic foam, with each bubble operating under its own physical laws. Some might contain stars and galaxies similar to ours, while others could be utterly alien, governed by forces we can't even imagine. Another intriguing version is the quantum multiverse, born from the strange world of quantum mechanics. According to this idea, every time a quantum event occurs, like the decay of a radioactive atom, the universe splits into multiple branches, each representing a different outcome. In one branch, the atom decays, in another, it doesn't. This branching process happens countless times every second, creating an ever-expanding tree of parallel universes. While this idea might sound like science fiction, it's a direct consequence of the mathematics behind quantum theory, offering a way to reconcile the randomness of quantum events with a deterministic universe. But why would scientists propose such radical ideas? One of the strongest arguments for the multiverse comes from the fine-tuning of our universe. The laws of physics as we know them seem perfectly calibrated to allow life to exist. If the strength of gravity or the charge of an electron were even slightly different, stars, planets, and life as we know it might never have formed. Some scientists argue that this fine-tuning is more than just luck, it's evidence that our universe is one of countless others, each with different physical constants. In this view, we simply find ourselves in a universe where the conditions are just right for life to thrive. Of course, the multiverse theory isn't without its critics. One major challenge is the lack of direct evidence. Since other universes, by definition, lie beyond our observable horizon, we can't see or interact with them. This makes the multiverse difficult to test, leading some to argue that it's more philosophy than science. Others point out that the multiverse doesn't necessarily solve the fine-tuning problem, it just shifts the mystery to a larger scale. If there are infinite universes, why do any of them have the right conditions for life? These questions remind us that the multiverse, while captivating, remains speculative, a frontier where science and imagination intersect. Despite its speculative nature, the multiverse has profound implications for our understanding of reality. It challenges the notion that our universe is unique, suggesting instead that we might be part of an infinite cosmic tapestry. This idea invites us to think bigger, to consider the possibility that the cosmos is far richer and more diverse than we've ever imagined. It also raises existential questions. If there are infinite universes, are there infinite versions of us? And if so, what does that mean for our sense of identity and purpose? As we ponder these questions, another fascinating concept comes into focus: time dilation, a real-world anomaly predicted by Einstein's theory of relativity. This phenomenon, where time passes differently depending on gravity and velocity, offers a glimpse into the strange and malleable nature of time itself. How does time dilation work, and what does it reveal about the fabric of reality? Let's explore. Imagine boarding a spaceship and traveling at nearly the speed of light. To you, time would feel normal, seconds would pass as they always do. But for someone watching from Earth, your clock would appear to tick slower, as if time itself were stretching. This bizarre phenomenon, known as time dilation, is one of the most mind-bending predictions of Einstein's theory of relativity. It tells us that time isn't a fixed, universal constant, but a flexible dimension that can warp and bend depending on speed and gravity. From the precision of GPS satellites to the mysteries of black holes, time dilation isn't just a theoretical curiosity. It's a real-world effect that shapes our understanding of the cosmos. At its core, time dilation arises from the interplay between space and time, unified in Einstein's framework as spacetime. According to his theory, the faster you move through space, the slower you move through time. This effect, called special relativistic time dilation, becomes noticeable only at speeds approaching the speed of light. For example, if you were to travel to a distant star at 99% the speed of light, you might experience just a few years passing on your ship, while decades or even centuries could elapse on Earth. It's a concept that challenges our everyday experience of time, showing how relative it truly is. But time dilation isn't limited to high-speed travel. It also occurs in the presence of strong gravitational fields, a phenomenon known as gravitational time dilation. Near massive objects like black holes or even Earth itself, time slows down compared to regions with weaker gravity. This effect has been confirmed by experiments with atomic clocks placed at different altitudes. A clock on a mountain where Earth's gravity is slightly weaker will tick faster than one at sea level. While the difference is tiny, it's measurable, and it has profound implications for technologies like GPS. Satellites orbiting Earth experience both the high-speed effects of special relativity and the weaker gravity of their altitude. If their onboard clocks weren't adjusted for time dilation, GPS accuracy would drift by kilometers within minutes. The implications of time dilation stretch far beyond navigation. For future space travelers venturing near the speed of light, time dilation could mean returning to an Earth that has aged far more than they have. It's a concept that blurs the line between science and science fiction, offering a glimpse into the extraordinary possibilities of relativistic travel. Yet, time dilation also raises deeper questions about the nature of time itself. Is time truly a universal constant, or is it a local experience shaped by our motion and environment? The answers lie in the fabric of spacetime, a dynamic and interconnected framework that underpins the universe. As we grapple with these questions, another fascinating aspect of spacetime comes into focus: gravitational waves. These ripples in the fabric of the cosmos, predicted by Einstein and first detected in 2015, are caused by massive events like the collision of black holes or neutron stars. Gravitational waves carry information about their sources, offering a new way to observe the universe. They also reveal how spacetime itself can stretch and compress, much like the surface of a pond disturbed by a thrown stone. Just as time dilation shows the flexibility of time, gravitational waves demonstrate the malleability of space, reminding us that the universe is far more dynamic than we've ever imagined. But what exactly are gravitational waves, and how do they connect to the anomalies we've explored? These ripples in spacetime are created when massive objects accelerate, sending out waves that propagate at the speed of light. Unlike light or other electromagnetic radiation, gravitational waves can pass through matter without being absorbed or scattered, making them a unique tool for observing the cosmos. Their detection has opened a new window into the universe, allowing us to hear events that would otherwise remain hidden. From the collision of black holes to the birth of neutron stars, gravitational waves offer a symphony of cosmic events, each one a testament to the dynamic and interconnected nature of spacetime. As we delve into the mysteries of gravitational waves, we're reminded that the universe is full of surprises. These ripples in spacetime, like time dilation, challenge our understanding of reality, inviting us to explore the boundaries of what we know. But the story doesn't end here. From the stretching of time to the warping of space, the universe continues to reveal its secrets, one anomaly at a time. What other cosmic puzzles await us, and how will they reshape our understanding of existence? Let's continue our journey into the unknown. Gravitational waves are like cosmic whispers, ripples in the fabric of spacetime that carry stories of the universe's most violent and energetic events. Picture dropping a stone into a still pond. The ripples that spread out are similar to how gravitational waves propagate through the cosmos. But instead of water, these ripples travel through the very fabric of reality, stretching and compressing spacetime itself. They're born from cataclysmic events like the collision of black holes or the merging of neutron stars, events so powerful that they send shockwaves across the universe. The story of gravitational waves begins with Albert Einstein, who predicted their existence in 1916 as part of his theory of general relativity. For decades, they remained a theoretical curiosity, a ghostly phenomenon that seemed impossible to detect. That changed in 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by capturing the first direct evidence of gravitational waves. The signal came from the collision of two black holes, each about 30 times the mass of our Sun, merging over 1.3 billion light-years away. This groundbreaking discovery not only confirmed Einstein's century-old prediction, but also opened a new window into the universe, a way to listen to cosmic events that had previously been invisible to us. Detecting gravitational waves is no small feat. LIGO observatories, located thousands of kilometers apart, use laser beams to measure infinitesimal changes in distance caused by passing gravitational waves. These changes are incredibly tiny, less than 1,000th the width of a proton. Yet, LIGO precision is so extraordinary that it can detect these minute distortions, allowing us to hear the echoes of black hole collisions and neutron star mergers. This technological marvel has revolutionized astronomy, giving us a new tool to explore the cosmos in ways we never thought possible. The significance of gravitational waves extends far beyond their detection. Unlike light, which can be blocked or absorbed by dust and gas, gravitational waves pass through matter unimpeded. This means they can carry information from the most extreme environments in the universe, such as the cores of supernova or the event horizons of black holes. By studying these ripples, scientists can learn about the properties of the objects that created them, shedding light on the nature of gravity, the behavior of matter under extreme conditions, and even the origins of the universe itself. One of the most exciting discoveries enabled by gravitational waves came in 2017, when LIGO detected the merger of two neutron stars. This event, observed not only through gravitational waves but also in light across the electromagnetic spectrum, marked the dawn of multi-messenger astronomy, a new era where we can study cosmic events using multiple types of signals. The collision of these incredibly dense objects, each just a few kilometers across but with more mass than our Sun, produced gravitational waves that rippled through space-time, followed by a burst of gamma rays, visible light, and even heavy elements like gold and platinum. This single event provided a wealth of data, deepening our understanding of how the universe creates and distributes the building blocks of matter. As we continue to listen to the whispers of gravitational waves, we're reminded of how interconnected the universe truly is. These ripples in spacetime connect us to the most distant and violent events, offering a symphony of cosmic collisions that shape the cosmos. But the story doesn't end here. Gravitational waves also lead us to another fascinating anomaly: neutron stars, the incredibly dense remnants of supernova that push the limits of physics as we know it. What secrets do these stellar corpses hold, and how do they shape the universe around them? Neutron stars are the universe's ultimate pressure cookers, born from the fiery death throes of massive stars. When a star much larger than our Sun exhausts its nuclear fuel, it collapses under its own gravity in a cataclysmic explosion known as a supernova. What remains is a neutron star, a stellar corpse so dense that just a teaspoon of its material would weigh billions of tons on Earth. These objects are the densest known in the universe, packing more mass than our Sun into a sphere no wider than a city. To put it into perspective, if you could stand on the surface of a neutron star, the gravitational pull would be so intense that it would flatten you into a thin, atomic layer in an instant. What makes neutron stars truly fascinating isn't just their density but their extreme properties. Many neutron stars spin at mind-boggling speeds, completing hundreds of rotations every second. This rapid spin, combined with their intense magnetic fields, can turn them into cosmic lighthouses known as pulsars. Pulsars emit beams of radiation from their magnetic poles, and as they spin, these beams sweep across the sky like the beam of a lighthouse. If Earth happens to lie in the path of these beams, we detect them as regular pulses of radio waves, X-rays, or even gamma rays. These pulsating signals are so precise that they rival atomic clocks in accuracy, making pulsars invaluable tools for studying the universe. But neutron stars aren't just celestial timekeepers, they're also laboratories for extreme physics. Their cores are thought to contain matter in states we can't replicate on Earth, with densities so high that protons and electrons merge to form neutrons. Some theories even suggest the presence of exotic particles or strange quark matter, a hypothetical state that could challenge our understanding of nuclear physics. The intense gravitational and magnetic fields around neutron stars also create environments where Einstein's theory of general relativity can be tested in ways impossible elsewhere. For example, the gravitational waves detected by LIGO often originate from neutron star collisions, offering a glimpse into the behavior of matter under such extreme conditions. Studying neutron stars, however, is no easy task. Their small size and immense distance make them difficult to observe directly. Instead, scientists rely on the radiation they emit, from radio waves to X-rays, to piece together their properties. Even then, the data can be challenging to interpret. The intense magnetic fields around neutron stars can reach trillions of times stronger than Earth's, creating environments where particles are accelerated to nearly the speed of light. These fields can also warp the star's surface, leading to phenomena like starquakes, massive shifts in the crust that release bursts of energy detectable across the galaxy. Neutron stars aren't just cosmic curiosities, they play a crucial role in the universe's evolution. When two neutron stars collide, they produce gravitational waves and scatter heavy elements like gold and platinum into space. These elements, forged in the extreme conditions of the merger, eventually become part of new stars, planets, and even life itself. In a very real sense, the gold in your jewelry or the platinum in your electronics might have originated from the collision of neutron stars billions of years ago. Among the most extreme members of the neutron star family are magnetars. These objects take the already intense magnetic fields of neutron stars and crank them up to unimaginable levels, up to 1,000 times stronger. Magnetars are so powerful that if one were located halfway between Earth and the Moon, its magnetic field would erase the data on every credit card on the planet. These extreme fields can produce bursts of X-rays and gamma rays, making magnetars some of the most energetic objects in the universe. Yet, despite their power, magnetars are also incredibly rare, with only a handful confirmed in our galaxy. The study of neutron stars and magnetars pushes the boundaries of our understanding of physics and the cosmos. These objects challenge us to rethink the limits of matter, gravity, and magnetic fields, offering a glimpse into the universe's most extreme environments. As we continue to explore these stellar remnants, we're reminded that the universe is full of wonders, each one more extraordinary than the last. But the story of extreme cosmic objects doesn't end here. Beyond neutron stars and magnetars lies another enigmatic phenomenon: quasars, the brightest objects in the universe powered by supermassive black holes. What are these luminous beacons and how do they shape the cosmos? Let's find out. Imagine a star so dense that a teaspoon of its material weighs billions of tons. And then imagine that same star surrounded by a magnetic field trillions of times stronger than Earth. This isn't science fiction, it's a magnetar, one of the most extreme and mysterious objects in the universe. Born from the explosive deaths of massive stars, magnetars are a rare type of neutron star, but they take the already mind-bending properties of neutron stars and amplify them to staggering levels. Their magnetic fields are so intense that if a magnetar were located halfway between Earth and the Moon, it could wipe the data from every credit card on the planet. These cosmic powerhouses are not just fascinating, they're windows into some of the most extreme physics in the cosmos. Magnetars form when a massive star, many times larger than our Sun, exhausts its nuclear fuel and collapses in a supernova explosion. What remains is a neutron star, but under specific conditions, that neutron star can develop an extraordinarily powerful magnetic field, transforming it into a magnetar. These magnetic fields aren't just strong, they're unimaginably strong, reaching up to 10 to the 15 times the strength of Earth's magnetic field. For context, that's strong enough to distort the structure of atoms themselves, creating conditions that defy our understanding of matter and energy. One of the most dramatic phenomena associated with magnetars is the starquake. Similar to earthquakes on Earth, starquakes occur when the crust of a magnetar shifts abruptly, releasing vast amounts of energy. But these aren't your average tremors. Magnetar starquakes can unleash more energy in a fraction of a second than the Sun emits in 100,000 years. These bursts of energy often manifest as gamma-ray flares, some of the brightest and most energetic events in the universe. In 2004, a magnetar in the constellation Sagittarius unleashed a gamma-ray burst so powerful that it temporarily ionized Earth's upper atmosphere, even though it was located 50,000 light-years away. That's the equivalent of feeling the heat from a matchstick held halfway across the galaxy. Studying magnetars is no easy task. Their rarity, only about 30 have been confirmed in our galaxy, makes them difficult to locate, and their unpredictable behavior makes them even harder to observe. Most magnetars are discovered through their gamma-ray bursts, which can be detected by satellites like NASA's Swift and Fermi missions. These bursts are fleeting, lasting only milliseconds to seconds, but they provide crucial insights into the extreme conditions on and around magnetars. Scientists also use X-ray telescopes to study the persistent X-ray emissions from these objects, which are generated by their intense magnetic fields heating the surface to millions of degrees. The extreme environments around magnetars also offer a unique laboratory for testing the laws of physics. Their magnetic fields are so strong that they can bend light in ways that challenge our understanding of optics. They can also accelerate particles to nearly the speed of light, producing streams of high-energy radiation that illuminate the surrounding space. These phenomena make magnetars invaluable for studying the interplay between magnetic fields, matter, and radiation in conditions that can't be replicated on Earth. Despite their rarity and the challenges of studying them, magnetars have a significant impact on their surroundings. Their gamma-ray bursts can influence the interstellar medium, the gas and dust between stars, by ionizing atoms and triggering the formation of molecules. They can also affect nearby stars and planets, potentially sterilizing any worlds within their reach with bursts of deadly radiation. In a sense, magnetars are cosmic sculptors, shaping their environments in ways we're only beginning to understand. As we delve into the mysteries of magnetars, we're reminded of the universe's capacity for extremes. These objects push the boundaries of what we thought possible, challenging us to rethink our understanding of matter, energy, and the forces that govern the cosmos. But the story of extreme cosmic phenomena doesn't end with magnetars. Their gamma-ray bursts, some of the most energetic events in the universe, also connect us to another fascinating cosmic mystery: gamma-ray bursts themselves. These fleeting but immensely powerful explosions are thought to originate from the deaths of massive stars or the collisions of neutron stars, and they offer a glimpse into the universe's most violent and energetic processes. What are these bursts and what can they tell us about the cosmos? Let's explore. Gamma-ray bursts are the universe's ultimate fireworks brief, blinding flashes of energy so intense that they outshine entire galaxies. In just a few seconds, a single gamma-ray burst can release more energy than the Sun will emit over its entire 10 billion-year lifetime. These cosmic explosions are among the most powerful events in the universe, and yet they remain shrouded in mystery. What causes such titanic outbursts, and what can they tell us about the cosmos? The story of gamma-ray bursts begins in the late 1960s, when military satellites designed to monitor nuclear tests detected mysterious bursts of gamma rays coming from deep space. At first, scientists were baffled. These flashes were unpredictable, appearing from random directions and lasting anywhere from milliseconds to several minutes. It wasn't until decades later, with the launch of satellites like NASA's Compton Gamma Ray Observatory, that astronomers began to piece together their origins. Today, we know that gamma-ray bursts come in two main varieties: long-duration bursts, which last more than 2 seconds, and short-duration bursts, which are over in a flash. Long-duration gamma-ray bursts are thought to occur when a massive star, many times larger than our Sun, exhausts its nuclear fuel and collapses under its own gravity. This collapse triggers a supernova explosion, but in some cases the star's core doesn't just collapse, it forms a black hole. As material spirals into the black hole, it creates jets of radiation that shoot out at nearly the speed of light. These jets, focused into narrow beams, are what we observe as gamma-ray bursts. The energy released is so immense that it can outshine the combined light of every star in its host galaxy. Short-duration bursts, on the other hand, are believed to originate from the merger of two neutron stars or a neutron star and a black hole. When these incredibly dense objects collide, they release a torrent of gravitational waves and gamma rays, creating a burst that lasts just a fraction of a second. The collision also produces heavy elements like gold and platinum, scattering them into space where they become the building blocks of future stars and planets. In fact, the gold in your jewelry or the platinum in your electronics might have been forged in such a cataclysmic event billions of years ago. Detecting gamma-ray bursts is no easy task. These events are fleeting, lasting only seconds, and they can originate from anywhere in the universe. Satellites like NASA's Swift and Fermi missions are constantly scanning the skies, waiting to catch the telltale flash of a burst. When one is detected, astronomers around the world spring into action, using ground-based telescopes to observe the afterglow, a fading trail of light that can reveal clues about the burst's origin and environment. This rapid response network has allowed scientists to study gamma-ray bursts in unprecedented detail, shedding light on some of the most extreme conditions in the universe. But gamma-ray bursts aren't just fascinating cosmic phenomena, they also have profound implications for life in the universe. If a gamma-ray burst were to occur too close to Earth, its intense radiation could strip away the ozone layer, exposing the planet to harmful ultraviolet rays from the Sun. Some scientists speculate that a nearby gamma-ray burst might have contributed to mass extinctions in Earth's distant past. Fortunately, such events are exceedingly rare, and the odds of one occurring in our cosmic neighborhood are slim. Still, gamma-ray bursts serve as a reminder of the universe's capacity for both creation and destruction. As we explore the mysteries of gamma-ray bursts, another cosmic anomaly comes into focus: fast radio bursts. These enigmatic signals, lasting just milliseconds, are thought to originate from distant galaxies, though their exact cause remains unknown. Like gamma-ray bursts, they offer a glimpse into the universe's most extreme environments, challenging our understanding of physics and the cosmos. What are these mysterious radio signals, and what secrets might they hold? Let's take a closer look. Fast radio bursts, or FRB, are one of the most perplexing phenomena in modern astronomy. Imagine a signal so powerful that it travels billions of light years across the universe, yet lasts only a few milliseconds less time than it takes to blink. These fleeting bursts of radio waves were first detected in 2007, and since then they've captivated scientists and stargazers alike. Unlike gamma-ray bursts, which come with a visible afterglow, fast radio bursts are invisible to the naked eye and can only be detected using specialized radio telescopes. Their brevity and intensity make them both fascinating and frustrating to study, as they vanish almost as quickly as they appear. The origins of fast radio bursts remain shrouded in mystery. Some theories suggest they could come from highly magnetized neutron stars known as magnetars, whose intense magnetic fields might produce these explosive signals. Others propose more exotic explanations, such as collisions between neutron stars or even the activity of advanced extraterrestrial civilizations. While the latter idea might sound like science fiction, it's a testament to just how baffling these signals are. The truth is, we still don't know what causes them, and that uncertainty is what makes FRBs so exciting to study. One of the most intriguing aspects of fast radio bursts is their ability to carry information about the universe itself. As these signals travel through space, they interact with the gas and dust between galaxies, leaving behind a unique fingerprint. By analyzing these fingerprints, astronomers can measure the density of the intergalactic medium, the vast, diffuse material that fills the cosmos. This makes FRBs not just cosmic curiosities, but also valuable tools for understanding the large-scale structure of the universe. They're like cosmic messengers, delivering clues about the environments they've passed through on their journey to Earth. Despite their potential, detecting and studying fast radio bursts is no small feat. Their fleeting nature means astronomers have to be incredibly lucky to catch one in action. To improve their chances, scientists have developed advanced telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, which scans large portions of the sky simultaneously. These efforts have paid off, with hundreds of FRBs detected in recent years, including some that repeat, offering a rare opportunity to study them in greater detail. Yet, even with these advancements, the true nature of fast radio bursts remains elusive, keeping astronomers on the edge of their seats. As we continue to unravel the mystery of fast radio bursts, another cosmic anomaly comes into focus: rogue planets. These wandering worlds, untethered to any star, drift through the darkness of interstellar space, their origins and fates as mysterious as the FRBs themselves. What are these solitary travelers, and how do they fit into the grand tapestry of the universe? Let's find out. Picture a planet drifting alone through the vast, cold expanse of space. No star to warm it, no solar system to call home. These solitary wanderers, known as rogue planets, are among the most enigmatic objects in the cosmos. Unlike the planets we're familiar with, rogue planets don't orbit a star. Instead, they roam freely through the galaxy, untethered and isolated like cosmic nomads. But how do these lonely worlds come to exist, and what secrets might they hold? Let's explore the fascinating story of rogue planets and their place in the universe. Rogue planets are thought to form in one of two ways. Some may start their lives like any other planet, born from the swirling disk of gas and dust surrounding a young star. But during the chaotic early days of a solar system, gravitational interactions with other planets or passing stars can fling a planet out of its orbit, sending it hurtling into the void. Others might form directly from collapsing clouds of gas and dust, much like stars, but without enough mass to ignite nuclear fusion. These planet-sized objects, sometimes called sub-brown dwarfs, are born free, never tied to a star in the first place. Regardless of how they form, rogue planets are left to drift through the galaxy, their journeys dictated by the pull of gravity and the randomness of cosmic motion. Detecting these dark wanderers is no easy task. Without a star to illuminate them, rogue planets are nearly invisible, their faint heat signatures the only clue to their presence. Astronomers rely on a technique called gravitational microlensing, where the planet's gravity bends and magnifies the light of a distant star as it passes in front of it. This fleeting event can reveal the planet's mass and distance, but it's a rare and fleeting opportunity. Despite the challenges, scientists have identified a handful of rogue planets, with estimates suggesting there could be billions more scattered throughout the Milky Way. One of the most intriguing questions about rogue planets is whether they could host life. At first glance, the idea seems far-fetched. Without the warmth of a star, these worlds are plunged into perpetual darkness and cold, with surface temperatures often hovering near absolute zero. But some rogue planets might have thick atmospheres or subsurface oceans heated by internal geothermal activity. In these hidden environments, life could potentially find a way to thrive, much like the extremophile organisms that inhabit Earth's deepest oceans or ice-covered lakes. While it's speculative, the possibility that life could exist on a rogue planet challenges our assumptions about where life might be found in the universe. Rogue planets also play a significant role in the galaxy's dynamics. As they drift through space, their gravitational influence can disrupt the orbits of other objects, potentially triggering collisions or altering the paths of comets and asteroids. Some scientists even suggest that rogue planets could act as cosmic seeds, carrying the building blocks of life from one star system to another. In this way, these lonely wanderers might be more than just curiosities. They could be key players in shaping the evolution of galaxies and the spread of life. As we ponder the mysteries of rogue planets, another fascinating category of worlds comes into focus: exoplanets. These planets, which orbit stars outside our solar system, have revolutionized our understanding of the cosmos, revealing a staggering diversity of worlds. From scorching hot Jupiters to rocky super-Earths, exoplanets offer a glimpse into the incredible variety of planetary systems that populate the universe. But how do these distant worlds compare to the rogue planets drifting through the darkness? Let's take a closer look. For centuries, humans have gazed at the stars and wondered, are there other worlds out there, perhaps like our own? The answer, as it turns out, is a resounding yes. Beyond our solar system, scattered across the galaxy, lie thousands of planets orbiting distant stars' worlds known as exoplanets. These celestial bodies, ranging from rocky super-Earths to colossal gas giants, have transformed our understanding of the universe. They challenge our assumptions, inspire our curiosity, and even hint at the possibility of life beyond Earth. But how do we find these distant worlds, and what makes them so fascinating? The search for exoplanets began in earnest in the 1990s, when astronomers developed innovative techniques to detect these elusive objects. One of the most successful methods is the transit technique, which looks for tiny dips in a star's brightness as a planet passes in front of it. Imagine standing in a dark room and watching a moth flutter in front of a light bulb. The bulb dims ever so slightly, just as a star does when a planet transits. This technique, used by missions like NASA Kepler and TESS, has uncovered thousands of exoplanets, revealing a stunning diversity of worlds. Another powerful tool is the radial velocity method, which measures the subtle wobble of a star as an orbiting planet tugs on it with its gravity. Think of it like a cosmic dance. The star and planet move in tandem, their gravitational pull causing the star to sway back and forth. By studying this wobble, astronomers can determine the planet's mass and orbit, piecing together its characteristics from light years away. Together, these methods have painted a vivid picture of the cosmos, showing us that planets are not only common but also incredibly varied. Among the most intriguing exoplanets are the rocky super-Earths, worlds larger than our own but smaller than gas giants like Neptune. These planets, often found in the habitable zones of their stars where temperatures could allow liquid water to exist, are prime candidates in the search for life. Take, for example, Proxima Centauri b, a super-Earth orbiting the closest star to our solar system. Located just over 4 light-years away, this world has sparked excitement and speculation. Could it host oceans, continents, or even life? While we don't yet have the answers, the possibilities are tantalizing. At the other end of the spectrum are the gas giants, massive planets like Jupiter and Saturn, but often far more extreme. Some, known as hot Jupiters, orbit perilously close to their stars, with scorching surface temperatures and atmospheres whipped into chaos by intense stellar winds. Others, like the infamous puffy planets, have incredibly low densities, making them resemble giant marshmallows floating in space. These bizarre worlds challenge our understanding of planetary formation, showing that the universe is far more creative and unpredictable than we ever imagined. The discovery of exoplanets has also reshaped our understanding of how planetary systems form. We've found systems with multiple planets packed tightly together, like peas in a pod, as well as lone planets orbiting stars at staggering distances. Some systems defy categorization altogether, with planets orbiting binary stars or even rogue planets drifting freely through space. This diversity suggests that the process of planet formation is far more complex than we once thought, influenced by a myriad of factors, from the composition of the protoplanetary disk to the gravitational interactions between planets. But the search for exoplanets isn't just about cataloging distant worlds, it's about answering one of humanity's oldest questions: are we alone in the universe? The discovery of potentially habitable planets has fueled the search for extraterrestrial life, driving missions to analyze their atmospheres for signs of oxygen, methane, or other biomarkers. Yet, despite the growing number of exoplanets and the tantalizing possibilities they present, we have yet to find definitive evidence of life beyond Earth. This raises a profound and puzzling question. If the universe is teeming with planets, why haven't we encountered any signs of intelligent life? This question lies at the heart of the Fermi paradox, a mystery that continues to challenge scientists and stargazers alike. The universe is vast, filled with billions of galaxies, each home to billions of stars and planets. With so many potential habitats, it seems almost inevitable that life, even intelligent life, should exist elsewhere. Yet, as far as we know, the cosmos is eerily silent. This puzzling contradiction is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everyone?" If the universe is so vast and ancient, why haven't we encountered any signs of extraterrestrial civilizations? This question has puzzled scientists and philosophers for decades, and the answers are as fascinating as they are unsettling. One of the most straightforward explanations is that intelligent life is exceedingly rare. While the universe may be teeming with simple, single-celled organisms, the leap to complex, intelligent life could be extraordinarily unlikely. Earth's history is filled with chance events, from the asteroid that wiped out the dinosaurs to the precise conditions that allowed human intelligence to flourish. If any of these events had unfolded differently, we might not be here to ponder the paradox. This idea, sometimes called the rare Earth hypothesis, suggests that while life itself might be common, the emergence of civilizations capable of interstellar communication could be a cosmic fluke. Another possibility is that intelligent civilizations do exist, but communicating across the vastness of space is far more difficult than we imagine. The distances between stars are staggering, and even signals traveling at the speed of light would take centuries or millennia to reach their destination. By the time a message arrives, the civilization that sent it might have long since vanished. Additionally, advanced civilizations might use technologies or communication methods we can't yet detect or understand, leaving us oblivious to their presence. It's like trying to find someone in a dark forest when they're using a flashlight we can't see. Then there's the darker side of the Fermi paradox, the possibility that intelligent civilizations inevitably self-destruct before they can make contact. Whether through war, environmental collapse, or technological catastrophe, it's possible that advanced societies reach a point where they can no longer sustain themselves. This idea, often referred to as the Great Filter, suggests that some critical barrier prevents civilizations from surviving long enough to become interstellar communicators. If this is true, it raises a sobering question. Are we, as a species, approaching our own Great Filter? But not all explanations are so bleak. Some scientists propose that advanced civilizations might simply have no interest in communicating with us. Imagine an ant colony trying to understand human technology. It's possible that extraterrestrial beings are so far beyond our comprehension that they see no need to interact with us. Alternatively, they might be deliberately avoiding contact, adhering to a kind of cosmic prime directive to let civilizations develop on their own. These ideas, while speculative, remind us that our assumptions about extraterrestrial behavior might be limited by our own perspective. The Fermi paradox isn't just a thought experiment, it has profound implications for humanity. If intelligent life is rare, it underscores the preciousness of our existence and the need to protect our planet. If the Great Filter lies ahead of us, it serves as a warning to navigate the challenges of the 21st century with care. And if civilizations are out there but remain silent, it challenges us to rethink how we search for them and what it means to be part of a larger cosmic community. To better understand the possibilities, scientists have developed tools like the Drake equation, a framework for estimating the number of communicative civilizations in our galaxy. By considering factors like the rate of star formation, the likelihood of planets in habitable zones, and the probability of life emerging, the equation offers a way to quantify our search for extraterrestrial intelligence. While the results are highly speculative, they provide a starting point for exploring one of humanity's oldest and most profound questions. Are we alone in the universe? As we continue to search for answers, the Fermi paradox reminds us that the cosmos is full of mysteries, each one a puzzle waiting to be solved. In our quest to understand whether we're alone in the universe, scientists have turned to a powerful tool, a mathematical framework designed to estimate the likelihood of intelligent civilizations beyond Earth. This tool is known as the Drake equation, named after astronomer Frank Drake, who first proposed it in 1961. At its core, the equation is a way to break down the vast, complex question of extraterrestrial life into smaller, more manageable factors. Each variable represents a step in the cosmic journey from star formation to the emergence of civilizations capable of communicating across the stars. But while the equation provides a structured approach, it also highlights just how much we still don't know. Let's break it down. The Drake equation multiplies several key factors together: the rate of star formation in our galaxy, the fraction of those stars with planetary systems, the number of planets that could potentially support life, the likelihood of life actually developing on those planets, the probability of that life evolving intelligence, the chance of intelligent life developing technology to communicate across space, and finally, the length of time such civilizations might exist. On paper, it's a straightforward formula, but every factor is filled with uncertainty. For example, while we've made incredible strides in discovering exoplanets, we still don't know how many of them are truly habitable. And even if life does emerge, how often does it evolve into intelligent, communicative beings? These are the kinds of questions that keep astronomers and astrobiologists up at night. One of the most debated variables is the probability of life developing intelligence. On Earth, life arose relatively quickly, but it took billions of years for complex organisms, let alone intelligent ones, to appear. Is this a common trajectory, or is Earth an outlier? Some scientists argue that intelligence might be a rare fluke, while others believe it's an inevitable outcome given enough time and the right conditions. Then there's the question of how long civilizations last once they develop the ability to communicate. Are they fleeting like a cosmic flash in the pan, or do they endure for millions of years? The answers to these questions could dramatically change the final estimate, ranging from millions of civilizations in our galaxy to just a handful, or even none at all. Despite its uncertainties, the Drake equation has played a crucial role in shaping the search for extraterrestrial intelligence, or SETI. It's a reminder that the universe is vast and filled with possibilities, but also that finding evidence of alien life will require patience, creativity, and a bit of luck. The equation also underscores the importance of interdisciplinary collaboration, bringing together astronomers, biologists, and even sociologists to tackle its many unknowns. And while we may not have definitive answers yet, the Drake equation continues to inspire us to ask the right questions. But as we ponder the possibilities of intelligent life, another intriguing idea emerges, one that could explain why we haven't found any signs of it yet. This concept is known as the Great Filter, a potential explanation for the Fermi paradox. If the universe is so vast and filled with potential, why does it seem so silent? The Great Filter suggests that somewhere along the path from simple life to advanced civilizations, there's a critical barrier that's incredibly difficult to overcome. Whether it's the emergence of life itself, the development of intelligence, or the survival of civilizations over long periods, this filter could be the reason we haven't encountered anyone else. But here's the unsettling part. We don't know if the Great Filter lies in our past or our future. If it's behind us, we might be among the rare few who have made it this far. But if it's ahead of us, it could mean that advanced civilizations are doomed to self-destruct before they can make their presence known. As we grapple with these possibilities, the Drake equation and the Great Filter remind us of both the promise and the peril of our cosmic journey. They challenge us to think deeply about our place in the universe and the choices we make as a species. Are we on the brink of becoming a truly interstellar civilization? Or are we destined to be a fleeting moment in the cosmos? The answers may lie not just in the stars, but in ourselves. What if the universe is teeming with life, but some invisible barrier, keeps civilizations from reaching the stars? This chilling idea is at the heart of the Great Filter hypothesis, a concept that tries to explain why, despite the vastness of the cosmos, we've yet to encounter any signs of intelligent extraterrestrial life. The Great Filter suggests that somewhere along the path from simple molecules to advanced civilizations, there's a critical hurdle so difficult to overcome that it effectively silences the universe. But where does this filter lie, and could it be ahead of us, threatening our own survival? To understand the Great Filter, let's break down the journey of life as we know it. It begins with the formation of planets in habitable zones where conditions might allow liquid water and the chemistry of life to emerge. From there, life has to arise, a process that, while seemingly common in theory, might be incredibly rare in practice. Even if life does appear, it must evolve into complex multicellular organisms and eventually intelligence. Finally, that intelligence must develop the technology to communicate across the stars and sustain itself long enough to do so. Each of these steps represents a potential filter, a point where the chain could break, leaving the galaxy silent. One possibility is that the Great Filter lies in the past. Perhaps the emergence of life itself is an extraordinarily rare event, or the leap from single-celled organisms to complex life forms is a cosmic fluke. If this is the case, it means we've already beaten the odds, and the universe might be largely devoid of intelligent beings. This would make Earth a rare jewel, a planet where life not only began but thrived and evolved into a civilization capable of looking to the stars. While this idea is comforting in some ways, it also underscores the fragility of our existence and the preciousness of life as we know it. But what if the Great Filter lies ahead of us? This is the more unsettling possibility. Perhaps the development of advanced technology inevitably leads to self-destruction, whether through nuclear war, environmental collapse, or some other catastrophic event. If this is true, it suggests that civilizations like ours rarely survive long enough to become interstellar. The implications are sobering. Every technological leap we make could bring us closer to our own downfall. This idea has led some to argue for caution in our pursuit of progress, urging us to prioritize sustainability and global cooperation to avoid becoming another casualty of the Great Filter. The Great Filter isn't just a theoretical exercise. It has real-world implications for how we approach the search for extraterrestrial life. If the filter is behind us, it means we might be alone or nearly alone in the universe. If it's ahead of us, it means we need to tread carefully, learning from the potential mistakes of civilizations that came before us. Either way, the Great Filter challenges us to think deeply about our place in the cosmos and the choices we make as a species. As we grapple with these profound questions, another tool emerges to help us understand the potential paths of intelligent civilizations, the Kardashev scale. This framework, proposed by Soviet astronomer Nikolai Kardashev, classifies civilizations based on their ability to harness and utilize energy, from Type I civilizations, which can harness all the energy of their home planet, to Type III civilizations, which can control the energy of an entire galaxy. The Kardashev scale offers a glimpse into the possibilities of technological advancement. Could humanity one day climb this scale, or will we be stopped by the Great Filter before we even reach Type I? The answers may lie in the choices we make today and the lessons we learn from the silent stars above. As we ponder the fate of civilizations and the mysteries of the cosmos, one framework offers a fascinating way to measure our progress or lack thereof. This is the Kardashev scale, a visionary concept proposed by Soviet astronomer Nikolai Kardashev in 1964. At its core, the scale classifies civilizations based on their ability to harness and utilize energy, offering a glimpse into the potential trajectories of technological and societal advancement. From controlling the energy of a single planet to mastering the power of an entire galaxy, the Kardashev scale isn't just a tool for imagining the future. It's a way to contextualize our place in the universe and the challenges we face as a species. So, where does humanity stand on this cosmic ladder, and what would it take to climb higher? Let's explore. The scale begins with Type I, or planetary civilizations, which are capable of harnessing all the energy available on their home planet. This includes energy from fossil fuels, nuclear power, solar radiation, wind, and even geothermal sources. For context, humanity currently sits at around 0.73 on the Kardashev scale, meaning we're not yet a fully fledged Type I civilization. While we've made incredible strides in energy production, from solar panels to nuclear reactors, we're still far from utilizing the full potential of Earth's resources. Achieving Type I status would mean mastering sustainable energy on a global scale, eliminating waste, and ensuring that our technological advancements don't come at the cost of our planet's health. It's a daunting challenge, but one that's increasingly urgent as we grapple with climate change and resource depletion. Moving up the scale, Type II civilizations are defined by their ability to harness the energy of an entire star. This is a leap so profound that it's almost beyond imagination. A Type II civilization wouldn't just use solar panels to capture sunlight. It might build megastructures like Dyson spheres, hypothetical constructs that encircle a star to capture its energy output. Such a civilization would have access to power levels millions of times greater than what we currently produce, enabling feats like interstellar travel, terraforming planets, or even creating artificial habitats on a colossal scale. The implications for science, culture, and exploration would be staggering, but so too would the challenges. Building a Dyson sphere, for example, would require materials and engineering capabilities far beyond anything we possess today. It's a vision that pushes the boundaries of what we think is possible, reminding us just how much further we have to go. At the top of the scale lies Type Roman 3, a galactic civilization capable of harnessing the energy of an entire galaxy. This level of advancement is so far beyond our current understanding that it's difficult to even conceptualize. A Type Roman 3 civilization might manipulate black holes, create wormholes for faster-than-light travel, or harness the power of billions of stars. The energy at their disposal would be truly astronomical, enabling them to reshape galaxies, transcend the limits of time and space, and perhaps even manipulate the fabric of reality itself. While this might sound like science fiction, it's worth remembering that just a few centuries ago, the idea of humans flying through the air or communicating instantaneously across the globe seemed equally fantastical. The Kardashev scale reminds us that the universe is full of possibilities if we're bold enough to reach for them. But the scale isn't just a tool for imagining the future. It also has profound implications for the search for extraterrestrial intelligence. If advanced civilizations exist, they might leave behind observable signs of their energy use, such as the infrared signatures of Dyson spheres or the gravitational effects of massive megastructures. By searching for these technosignatures, scientists hope to identify evidence of Type Roman 2 or Type Roman 3 civilizations, offering clues about the potential trajectories of intelligent life. Yet, the absence of such signs raises questions too. If the universe is so vast, why haven't we detected any galactic-scale energy use? Could it be that the great filter lies between Type Roman 2 and Type Roman 3, preventing civilizations from reaching that level of advancement? These questions remind us that the Kardashev scale isn't just a measure of energy, it's a lens through which we can explore the possibilities and challenges of intelligent life in the cosmos. For humanity, the Kardashev scale is both an inspiration and a cautionary tale. On one hand, it invites us to dream big, to imagine a future where we've mastered the energy of our planet, our star, and even our galaxy. On the other, it challenges us to confront the obstacles that stand in our way, from environmental degradation to the potential for self-destruction. Achieving even Type I status will require unprecedented levels of global cooperation, innovation, and foresight. But if we succeed, the rewards could be beyond anything we've ever imagined. As we contemplate these possibilities, another intriguing concept comes into focus. Dyson spheres, the hypothetical megastructures that could enable a civilization to harness the full energy of a star. These colossal constructs, first proposed by physicist Freeman Dyson, represent the kind of audacious thinking that the Kardashev scale inspires. But what exactly are Dyson spheres, and could humanity ever build one? Let's dive into this fascinating idea and explore what it might mean for our future. Imagine a structure so vast that it could encircle an entire star, capturing nearly all of its energy output. This is the essence of a Dyson sphere, a hypothetical megastructure first proposed by physicist Freeman Dyson in 1960. The idea is as bold as it is ambitious. A civilization advanced enough to build such a structure would have access to unimaginable amounts of energy, enabling feats like interstellar travel, terraforming planets, or even creating artificial worlds. But what exactly is a Dyson sphere, and why does it captivate scientists and science fiction enthusiasts alike? Let's dive into this fascinating concept and explore what it might mean for the future of intelligent life in the universe. At its core, a Dyson sphere is a theoretical construct designed to harness the energy of a star. Freeman Dyson envisioned a swarm of satellites or panels orbiting a star, collectively capturing its light and converting it into usable energy. Unlike a solid shell, a common misconception, a Dyson sphere would likely consist of countless individual components, forming a network that surrounds the star. This design avoids the immense structural challenges of a single, rigid structure while still achieving the goal of energy capture. The energy harvested could power entire civilizations, providing a near-limitless supply of resources for technological and societal advancement. The concept of Dyson spheres isn't just a thought experiment. It's also a potential tool for detecting advanced extraterrestrial civilizations. If a civilization were to build such a structure, it would emit a distinct infrared signature as the captured energy radiated into space. This waste heat would stand out against the cold backdrop of the cosmos, serving as a telltale sign of technological activity. Scientists have already begun searching for these infrared signals, scanning the skies for evidence of Dyson spheres or similar megastructures. While no definitive proof has been found yet, the search itself is a testament to humanity's curiosity and determination to uncover the mysteries of the universe. But building a Dyson sphere is no small feat. The engineering challenges are staggering, requiring materials and technologies far beyond our current capabilities. For instance, constructing even a single panel of a Dyson swarm would demand an astronomical amount of raw materials likely harvested from asteroids, moons, or even planets. Additionally, the energy required to assemble and maintain such a structure would be immense, raising questions about how a civilization could achieve this without depleting its resources. These challenges highlight the vast gulf between our current technological level and the capabilities required to build something as ambitious as a Dyson sphere. Despite these hurdles, the idea of Dyson spheres continues to inspire. They represent a vision of what humanity, or any intelligent species, might achieve given enough time, ingenuity, and cooperation. They also remind us of the sheer scale of the cosmos and the potential for civilizations far more advanced than our own. As we search for signs of these megastructures, we're not just looking for evidence of alien life, we're exploring the limits of what's possible, pushing the boundaries of science and imagination. While the search for Dyson spheres remains ongoing, another cosmic mystery has captured the attention of astronomers: the WOW signal. Detected in 1977, this brief but powerful radio burst has puzzled scientists for decades. Unlike the steady hum of a Dyson sphere's infrared signature, the WOW signal was a fleeting, enigmatic event, one that has yet to be fully explained. What could have caused this mysterious signal, and could it be a clue to the existence of intelligent life? Let's turn our attention to this intriguing anomaly and explore what it might reveal about the universe's hidden secrets. On August 15, 1977, a radio telescope in Ohio picked up something extraordinary, a signal so powerful and unusual that it left astronomer Jerry Amon scrawling, "Wow." In the margins of the data printout, this exclamation, now immortalized as the WOW signal, remains one of the most tantalizing mysteries in the search for extraterrestrial intelligence. For 72 seconds, the Big Ear radio telescope detected a strong, narrowband radio signal coming from the direction of the constellation Sagittarius. The signal was unlike anything astronomers had ever encountered. It was intense, focused, and seemingly artificial in nature. But as quickly as it appeared, it vanished, leaving behind more questions than answers. The WOW signal stood out for several reasons. First, it was a narrowband signal, meaning it was concentrated at a specific frequency, around 1420 MHz. This frequency is significant because it falls within the water hole, a range of radio waves that scientists consider ideal for interstellar communication. This region is relatively quiet, with minimal interference from natural cosmic sources, making it a logical choice for any civilization trying to send a message across the stars. Second, the signal was incredibly strong, reaching 30 times the background noise level. For a brief moment, it seemed to be a deliberate beacon, a cosmic hello from another world. Despite its intriguing characteristics, the WOW signal has never been detected again, despite numerous attempts to locate its source. Over the years, astronomers have scanned the same region of the sky, hoping to catch another glimpse of this enigmatic signal. But the silence has been deafening. Some have speculated that the signal could have come from a passing satellite or a natural celestial phenomenon, but no explanation has fully accounted for its unique properties. The lack of repetition has only deepened the mystery, leaving the WOW signal as a tantalizing, one-hit wonder in the annals of astronomy. The implications of the WOW signal are profound. If it was indeed a message from an extraterrestrial civilization, it would be the first concrete evidence that we're not alone in the universe. It would also suggest that other intelligent beings are actively trying to communicate, possibly using technologies we can recognize and understand. On the other hand, if the signal has a natural explanation, it challenges us to rethink what we know about cosmic phenomena and the limits of our current detection methods. Either way, the WOW signal serves as a reminder of how much we still have to learn about the cosmos. The enduring mystery of the WOW signal has inspired countless theories and debates, but it also highlights the challenges of searching for extraterrestrial intelligence. Interpreting such signals requires patience, precision, and a willingness to entertain possibilities that stretch the boundaries of our understanding. It also underscores the need for better tools and techniques to detect and analyze potential signs of alien life. As we continue to scan the skies, the WOW signal remains a beacon of hope, a reminder that the universe is vast, full of surprises, and perhaps, just perhaps, teeming with life waiting to be discovered. As we ponder the mysteries of the WOW signal, another cosmic enigma comes into focus, one that arrived in our solar system unannounced and left us with more questions than answers. This is Oumuamua, the first known interstellar object to pass through our cosmic neighborhood. Unlike the WOW signal, which was a fleeting burst of radio waves, Oumuamua was a tangible visitor, a strange, elongated object that defied easy classification. What secrets does this interstellar traveler hold, and could it be another clue in our search for life beyond Earth? Let's explore. In 2017, something extraordinary streaked through our solar system, a visitor from beyond the stars. This mysterious traveler, named Oumuamua, was the first known interstellar object ever detected passing through our cosmic neighborhood. Its name, derived from the Hawaiian word for scout or messenger, couldn't have been more fitting. Unlike the familiar comets and asteroids that orbit our sun, Oumuamua came from somewhere else entirely, carrying with it secrets from the depths of interstellar space. But what made this object so remarkable wasn't just its origin, it was its bizarre and baffling characteristics. The first thing astronomers noticed about Oumuamua was its shape. Most asteroids and comets are roughly spherical or irregular, but Oumuamua was elongated, stretching an estimated 800 meters in length while being only about 80 meters wide. Imagine a cosmic cigar tumbling through space, its surface reflecting sunlight in strange, uneven patterns. This unusual shape made it unlike anything we'd ever seen before, sparking immediate curiosity and debate. How did such an object form, and what could it tell us about the processes at work in other star systems? But the surprises didn't stop there. As Oumuamua sped away from the sun, astronomers observed something even more puzzling. It was accelerating. Objects in space are governed by gravity, so their trajectories are predictable. Yet Oumuamua seemed to be defying this rule, gaining speed in a way that couldn't be explained by the sun's gravitational pull alone. This non-gravitational acceleration led to a flurry of theories. Some suggested it might be outgassing, releasing gas like a comet, but no visible tail or coma was detected. Others proposed more exotic explanations, including the possibility of solar radiation pressure acting on an incredibly thin, lightweight structure. And then, of course, there was the wilder speculation. Could Oumuamua be something artificial, like an alien probe or spacecraft? The idea that Oumuamua might be of extraterrestrial origin captured the public's imagination, though most scientists remained skeptical. Harvard astronomer Avi Loeb famously argued that its unusual properties, particularly its acceleration and shape, warranted serious consideration of the possibility that it could be a piece of alien technology. While this theory is far from proven, it highlights the profound questions Oumuamua raises about the nature of interstellar objects and the potential for intelligent life elsewhere in the universe. After all, if Oumuamua is natural, it suggests that other star systems produce objects unlike anything in our own solar system. And if it's artificial, well, that would change everything. As Oumuamua receded into the darkness, it left behind more questions than answers. Its brief visit was a reminder of how much we still have to learn about the cosmos. Could there be more interstellar objects like it drifting unnoticed through our solar system? And what might they reveal about the formation of other planetary systems, or even the possibility of life beyond Earth? These questions have spurred new efforts to detect and study future interstellar visitors, using advanced telescopes and observational techniques to catch them before they slip away. From the Great Attractor's gravitational pull to the fleeting whispers of fast radio bursts, and now to the enigmatic Oumuamua, the universe continues to surprise us with its mysteries. Each anomaly challenges our understanding, pushing us to rethink what we know about space, time, and the forces that shape the cosmos. As we piece together these cosmic puzzles, we're reminded that the universe is far stranger and far more wondrous than we ever imagined. And with every discovery, we take one step closer to unraveling its deepest secrets. As we bring our journey through the cosmos to a close, it's worth pausing to reflect on the extraordinary anomalies we've explored, from the gravitational enigma of the Great Attractor to the fleeting, mysterious signal from beyond known as the WOW signal and the interstellar traveler Oumuamua that defied all expectations. Each of these cosmic puzzles has challenged our understanding of the universe, pushing the boundaries of what we thought possible and reminding us just how much remains unknown. These anomalies aren't just oddities, they're signposts pointing us toward deeper questions about the nature of space, time, and our place within it all. Take the Great Attractor, for instance, a gravitational force so immense that it's pulling entire galaxies toward it, yet hidden behind the veil of our own Milky Way. Its existence forces us to rethink the large-scale structure of the universe and the role of dark matter in shaping it. Then there's dark flow, the peculiar motion of galaxy clusters that suggests an unseen force beyond our observable universe, hinting at the possibility of other realms or dimensions we can't yet perceive. These phenomena remind us that the universe is far more interconnected and far stranger than we've ever imagined. And what about the cosmic voids, those vast stretches of emptiness where galaxies refuse to form? These regions aren't just empty space, they're active players in the universe's expansion, influencing the fate of everything around them. They challenge our assumptions about the distribution of matter and the forces that drive the cosmos. Even on the smallest scales, quantum fluctuations ripple through the fabric of space-time, seeding the universe with the potential for galaxies, stars, and life itself. These microscopic ripples remind us that the universe is dynamic and alive, constantly evolving in ways we're only beginning to understand. Of course, we can't forget the extremes: black holes, neutron stars, and Magnetars, objects that test the limits of physics and our imagination. From the event horizons of black holes, where the laws of physics break down, to the unimaginable densities of neutron stars, these cosmic phenomena are laboratories for exploring the most extreme conditions in the universe. And then there's the tantalizing possibility of wormholes and white holes, theoretical constructs that could rewrite our understanding of space and time, offering shortcuts through the cosmos or even gateways to other universes. But perhaps the most profound question of all is the one that ties these anomalies together. What do they tell us about the universe and ourselves? Each discovery, each mystery, invites us to rethink what we know and to ask new questions. They remind us that science isn't just about finding answers. It's about embracing the unknown and daring to explore the edges of our understanding. As Carl Sagan once said, somewhere, something incredible is waiting to be known. These words resonate deeply as we stand on the brink of new discoveries, armed with ever-advancing technology and an insatiable curiosity. So, as we conclude this exploration of the universe's most unusual anomalies, let's not see this as an ending, but as an invitation to keep exploring, questioning, and marveling at the cosmos. The mysteries we've uncovered are just the beginning. There's still so much to discover, so many questions waiting to be asked, and who knows, the next great anomaly could be just around the corner, waiting to challenge everything we think we know. Thank you for joining me on this cosmic journey. If you've enjoyed this deep dive into the fabric of space, don't forget to share your thoughts in the comments below and subscribe for more explorations into the wonders of the universe. Together, let's continue to uncover the incredible, because the universe is full of surprises, and the best